Hi, in this video I wanted to share how I designed and implemented this bipedal humanoid robot. It's running a policy model trained in Isaac Lab, and it has 10 degrees of freedom. And here is the back view of the robot. Most of the parts were 3D printed and some parts were made from bent stainless steel sheet metal. And here we see it from the side here, and I will explain the parts a little bit later in the video. There we go. So the first test is a stability test. The policy was trained to keep the robot in balance, so I'm pushing it and the robot returns back to a stable point. I'm not pushing it too hard because I've had too many plastic parts break, so I'll show a video of it a little bit later. This is my experiment area, and here you can see I don't really have a lot of space for walking, so you'll have to excuse me for not showing a long walking cycle. So here is the robot walking in policy, and it stepped on my foot, but it's figured out it's not a problem for the robot. It will balance itself even if it steps on me. And here we go. We'll walk it out of the frame, and you'll hear it collide with the object out of, yeah, there we go, the metal frame. Here I've run some tests of the robot walking and then going back to a standing pose. There we go. So there's a sudden jerk from walking to standing because it switches policies. Standing policy and balance policy are two separate policies. So. And in this case, it balanced pretty nicely. And here is some examples of walking and standing. And I am controlling the robot using my controller in my hand. So I have to make sure the robot doesn't fall down, and then also try to make it walk forward at the same time. Let's take a look at a failure case. So here we'll see the robot lose balance, and I'll discuss the failure cases a little bit more a little bit later. But the main reason turns out to be because I used plastic, and I'm using the controller to change the orientation of the IMU during online. So it also it affects the training. And here is an example of the robot breaking the plastic part. You'll see how easily the plastic parts break if I push it too hard. Yeah, very easily it breaks. Let's talk about the design of the robot next. The robot is made out of 10 motors, so it has 10 degrees of freedom. The two motors here, which is the hip x-axis rotation and z-axis rotation, these are Robstride RS06 motors. They're rated at 11 Newton meters and a peak load of 37 Newton meters. And then the two main motors are the hip pitch angle and the knee joint angle, which was the Robstride 03, which has a peak load of 60 Newton meters. And here we can see the cables, which are kind of daisy chained through the motors. So it starts from the top and then connects each motor on one end and then comes out the other end. All of the cables are made from XT30 or XT30 PB for the power cables, and then the CAN network cables are CAN high and CAN low cables, which are also daisy chained like this. And then the two ankle motors are the Robstride RS02, which has a peak load of 17 Newton meters. And I can't show it here, but at the end of the each CAN network, I have 120 ohm terminal resistors to stabilize the CAN networks. So here is the top section of the robot. The robot is made of 30 by 30 aluminum profile. And here we see the two batteries that is powering the robot. These are LiPo batteries, 6S, with a total capacity of 2200 milliamp hour, and there's two of them, so I've connected them in series, giving me 48 volts. And here we have the IMU unit at the center here, kind of hard to see, but this is an LSM6 TSOX IMU unit right there. On the back here we have a buck converter. This one is taking the 48 volt from the battery and then converting it to 19 volt for the computer. And the computer for this project, which is kind of hard to see here, is the Jetson AGX Xavier, which takes 19 volts. And on the side here we have the power distribution board. Everything uses a XT90 connector. Here is the input power, and then this one is connected to the buck converter, and then it's powering the Jetson right here. And then these two connectors are powering each of the two legs. So this one may be a left leg, and then this is the right leg here. Now we have a mess of cables here. These are the connections to the 40-pin connectors on the Jetson, and on one of them is the CAN transceiver, which connects the left leg, and then the other one is a CAN transceiver that connects to the right leg. The IMU unit is also connected to the 40-pin connection. The IMU unit needs 3.3 volts, so I also have a buck converter that takes 5 volts from the 40-pin connection and then drops it down to 3.3 volts. So here are the parts that connect the motors. This part here, the black one here, and this one here are made out of stainless steel sheet metal, which had to be ordered online. So in my case, I ordered them from JLC CNC, and then everything else is 3D printed. So here are some examples. So for example, this part here is a connector for the knee, and then this one is the connector for, well, the Z-axis of the hip rotation. And I printed everything using setting wall loops to 999. If you don't know what that means, it just means that there is no gaps inside the print. It's basically a solid block of plastic. Here is the full schematic of the robot's electronics. We have the battery at 2 batteries, giving us a total of 48 volts. It goes into the power distribution board. The power distribution board powers the left and right legs, which are the Robstride motors here. Then another lead connects to the buck converter that powers the Jetson Xavier using 19 volts. Now the 40-pin connectors, which are shown here, have these connections. So the top two one are the CAN transceivers. The red one is the power, and the blue one is the data line. So the 40-pin is powering the transceiver and also transmitting and receiving network signals from the transceiver here. This transceiver will connect to the left leg, and then the second transceiver will connect to the right leg here. Now the IMU unit is talking directly to the Jetson using the 40-pin connector, but the powering is done using buck converter that converts 5 volts to 3.3 volts for the IMU, and it looks like this. So here is the robot, design of the robot. I've designed it in Onshape. Here is what the robot assembly looks like, and if we take a look at the total weight of the robot, it's 14.1 kilograms, and this point here is the center of mass. So if we look at it from the side, it's kind of well balanced at the center here. The height of the robot, which we can kind of measure, so from the top here to the legs here, is exactly, well, 1 meter basically. So the height of the robot is 1 meter. There we go. And this project is, I have a free account on Onshape, and the project name is Bipedal rope stripe. So if you just go on Onshape, you can just search for this, and you can actually see the whole project. if you're interested, my username is right here. So for those who are interested, you can take a look at the project. And I've designed the robot here, and then 3D printed the parts that needed to be 3D printed. Here is the URDF file that's exported from Onshape. Here is the design of the robot. Now the origin of the robot is right here, which is actually the IMU unit, or rather the IMU chip, which is right here. So the 000 point is actually corresponding to the 000 point of the IMU here, and which is quite nice when you start to use IMU in your simulation. Here we have the two batteries, and on the back here is the buck converter for the Jetson unit, which is right here. I've colored the motors in red so we can easily see them, and all the black parts are either 3D printed or sheet metal parts. Right? And we can take a look at the joint limits. So I've set the joint limits inside the URDF file, and it looks something like this. I've set them basically on what looks reasonable to me, but also I don't want the angle to be too large so that the plastic parts can break. Now the important thing we need to look at here is the colliders. Oops. Here's the colliders for the robot, and if I remove the visuals, the colliders are primitive shapes, and you can see everything on the inside is gone, and then all the other parts are very simplified colliders that look like this. The important one is the shoes here. Now if I turn on the shoes, you can see the shoe has a curvature on the side here, like this and like this. And if I remove the visuals, it's modeled as two cylinders. Next, let's import the URDF file to IsaacSim. This is a movable base, and we can ignore all of this and replace cylinders with capsules and allow self-collisions. Now we can import this, and the replace cylinders with capsules option actually does quite a lot of things here. So you can see all the cylinders have been replaced with these capsules, and more importantly, you can see here on the legs, those cylinders now have a rounded curve at the edge of the shoes here, and this matches the design of the shoe. The middle section is actually, well, it doesn't have a collider in the middle, but I don't think it's possible to touch the ground with this part when the ground is actually flat. So this collider works out fine. So if we hit play, one problem you will immediately see is it starts to it will do a split, and the reason for that is we have to, the collider on the robot is now starting to collide with itself, so we have to disable self collisions here, and you see it falls over. Next thing I wanted to discuss is how I've decided the gains on the robot. So to do this, I've modified the physics scene. First I'm going to disable gravity, so when I press play, it's not going to play. Then I'm going to look at robotics gain tuner. There we go. So this is what's going to allow me to take a look at what my gains on the robot should be set to. So currently it's set to some value by default, and I'm going to set this. Well, let's take a look at what this does first. So let's set this to, let's say, a 2-second test. Remove all the extra ones. Okay, but let's just test this one. Press play and then press run test. So you can see here, this by default creates well, the gains by default create this kind of motion where the dark blue one is the joint we want, and then the pale blue one is the actual position of the joint. Now the problem here is I had the plastic breaking easily, so I wanted to kind of limit the amount of acceleration that the joint can reach. So to do that, I've set my stiffness to a small number, and then I've set the damping to a large number. And if I run test, it still moves okay, but you'll see it lags behind a little bit, and this is kind of limiting. So for example, if the policy is outputting very erratic actions, then this should kind of work by limiting the amount of acceleration this should experience. And in actual training, I've set this to a value of 8, which it still looks quite reasonable, and we can see that it's a little bit late, but it does work in my favor, in my opinion. In my previous video, I used a camera to capture motion, walking motion data from myself, and then I've transferred that to my robot to generate walking motion. In this time, I'm using a program called Humanoid. Humanoid is a program that allows generating motion capture data from text input. So here is what it looks like. Here I've set the model as the unitary G1, and then I can ask Humanoid to generate motion. So for example, like for the first 2 seconds, I can tell it to generate standing still data, and then after that walking forward data. So if I hit generate, it will generate the motion data. Looks like this. So it was standing, and then it will start walking like this. So I can take this walking animation, and then I can transfer it to my robot and get a walking animation data for training. So here is what the data looks like on my custom robot. There we go. So initially it's standing still, and then it will start to walk like this. Now you can see that the data is not very clean. The robot is swinging left and right too much, and also I need one motion cycle, not the continuous data like this. So that means I need to post-process it a little bit. So after post-processing, the walking animation looks like this. So as you can see, it's smoothed quite a bit, and it is only just one walking cycle, which is what I need for Isaac Lab training. In my previous video, I've showed how to train the policy for the humanoid model. Not very much has changed from that video, so I'll quickly go over the configuration for Isaac Lab here. Now I've trained 2 policies. One is the walking policy, and then the other one is the standing policy. There is very little difference between these two. So the walking policy has animation tracking rewards, and the standing one doesn't have it. So converting from the walking to standing is simply just remove the parts related to the walking and animation. My animation has been collected at well, actually 90 FPS, but I want to slow down the animation, so the walking animation is a little bit slower. So I've set it to 80, and then the number of frames is 120 frames of walking animation. Here is my robot articulation configuration. I'm using a delayed PTE actuator configuration here with a minimum delay of 1 and maximum delay of 6. Now something that's important here is this is the delay on the physics step and not the environment step. What that means is the delay is, my policy is trained at 50 Hertz. So that means each environment step is 20 milliseconds. but the physics step has a decimation of 4, so that means each physics step is done at 5 milliseconds. So what this means is minimum delay of 1 means 5 millisecond delay, or maximum delay of 60 means 30 millisecond delay. So this is not delaying by 6 environment steps, but physics steps. Just important distinction here. The RS03 motor is the hip and the knee joints set here. I've set the max effort to 60 Newton meters and max velocity, which is also on the spec sheet of the motor set here. And I've already explained how I set the stiffness and damping. Actually, I've tried to tune my motor by collecting data from the motor and then comparing it to the joint angle, and it turned out actually the difference is quite minimal, quite small. So just using some domain randomization, I think, is enough to deal with the small difference between simulation and the robots, the motor's actual damping and stiffness. For the RS06 motor, I've set it to the spec sheet values here. I've just set a little bit of a different gain and damping here, and on the ankle one has a bit of a less damping compared to the other motors. Here is the terrain. I've set the friction to be quite high, and later we'll see that this is a bit of a problem, but not too much. The reason why I've set it to be quite high is because the contact point of my legs is just 2 cylinders. It's not the whole foot surface. So that's why it doesn't translate well. Maybe I should create an additional collider for the foot and then drop this down, but for this time I've used these values. Here is the IMU. I've used IMU as part of the training. The IMU is actually positioned at 0, 0, 0 because I've set the IMU as the origin of the robot, and the gravity bias is set to these values. The output of the policy is applied as joint position action with a scaling factor of 0.25. Here is the observation for the policy and the critic. So the policy has very few observations. This one is joint position and joint velocity. I've added some noise to it to simulate domain randomization. Here is the last action. Base angle to target is a parameter that tells the robot how much it needs to turn. So it's basically just an angle represented in radians. And motion phase is the phase of the motion using the cyclic representation, which is the sine and cosine. I've explained this in my previous video if you have any questions. So the main feature for training is IMU features, and we can take a look at what this actually is. So at the end of all of this calculation, it only has 2 actual information. This is the raw IMU observation. So this contains acceleration and gyroscope rotation, rotational velocity. And then the other one is the gravitational vector, which is estimated from the acceleration and gyroscope IMU data. And so all of this here is calculating the gravitational vector, but I've manually implemented something called the Mahoney filter. So you don't really need to do this, just look up Mahoney filter and then copy the code in. But the point is the IMU feature is simply the raw IMU data plus the estimated gravity vector. Now, on the other hand, the critic sees basically all information that's available to it from the simulation. So it sees the base linear velocity, base angular velocity, base yaw pitch and roll, base up projection, joint velocity, joint action, last action, and it also has feet contact state, which is quite nice. And then you just pass these 2 as the policy and the critic. As for events, I have a lot of randomization on the event. So on reset, it resets the position and velocity of joints. It applies external torque. It also pushes by applying a velocity. There's another push, which is interval-based pushing, and just randomize the joint state on reset here. As additional domain randomization, I have randomizing rigid body mass, which is the center of, well, the total mass of the robot is added. So here is the range. Center of mass of the body is also modified with this range, and then the actuator gain is modified. Finally, the rewards, which is probably the most important one here, is the, which is well, here it is. I have progress. Progress is rewarding how, you know, the robot walking towards the target. The alive term. These are penalties. How much torque is being used, penalize, and then joint acceleration penalty and action rate penalty. This one is the animation tracking penalty. So I've already showed this in my last video, so take a look if you're interested. So basically this is tracking the animation, so the motion capture data, and then the current angles of the robot, and then the required angles of the motion capture data. And this is the joint velocity tracking. So again, from the motion capture data, I can also generate the joint velocities and then tell the robot to track those values. Move to target is again also a value that tells the robot to turn and then move to target. Feet contact tracking is a new one. So this one, I know that the robot needs to lift the leg at some well, time in the animation. So here I penalize the robot if the foot is in contact with the ground while it's, you know, the animation is telling it that it should not be in the ground. These ones are probably not that important, but here this one penalizes the robot for having x and y angular velocity. So basically it needs to keep the body straight. This is a penalty for not having the body in a flat orientation. So if it has non-zero x and y rotation, again you penalize this, and this will penalize the robot for moving left and right. Feet slide will kind of discourage the robot from sliding the feet on the ground, and then here is a feet lift reward. So basically if the robot well, the robot will get a reward if it lifts the weight above 3 centimeters. So let's take a look at how training progresses. At step 0, obviously it cannot balance, so it fall over. At basically step 10,000, you can see it's learned to balance, but it's, you know, it's trying to copy the animation, so it's bending the knees, but it hasn't figured out how to actually walk yet. At 20,000, it's kind of learned how to lift its leg, and it's also kind of turning towards the target direction, so which is x at 1,000. And at step 30,000, it's getting slightly better. It turns towards target and then it tries to walk. Here we have at 40,000, it's learning how to take steps. Not that well, but it's getting there. Let's skip ahead to maybe 70,000. So it's learned how to basically walk, but the entropy of the training is so high that it experiences too much errors or kind of action output, so it's not very stable yet. Also, there is an interval-based push, so we might actually see them getting pushed. Maybe let's see if this one gets pushed. I guess that one got pushed. Now the problem here is it's swinging left and right, and the reason why this swing happens is because of the errors introduced in domain randomization, and that causes it to. So if the the manual randomization is lowered, then this stepping left and right will become better. So at 150,000, it kind of looks okay as a walking step. Now, if we look at the training progress, here is what it looks like. So this, the current one we just saw is the yellow curve here, and this is the action rate and alive animation tracking. The important one I wanted to show you is the mean noise. So the noise is the output of the policy's action. No, the action of the policy has an extra noise added to it, so that it explores different, different joint angles as an action. But we want to drop it significantly so that it kind of finalize the training. So this is done using the configuration file for the RSL BPO. So here is what my configuration for initial training looks like. This is the size of my actor and critic, but the point I wanted to go over is this value, learning rate, and desired KL divergence. KL divergence is the value that's actually giving it a lot of noise the policy is experiencing. So basically you want to drop it to something like maybe half, and entropy is also the same, so you also want to reduce it to half. Now after about 3 hours of training, the learning rate is too high, so you want to drop it to about -5, and number of learning epochs. So when the policy collects data, it trains on that data 5 times, and then it generates the next set. So at this stage it's probably overstepping if you train on it on one batch too much, so I drop it down to 3, and then I resume training. And so if I resume training with this setting, we will immediately see that the output of the policy will start to stabilize. So here is resumed training, and before it was kind of, not balancing very well, but then with the new settings you'll see that it becomes much more confident in its steps. Oh, that one got pushed right there. There we go. At maybe 80,000 here. So this is kind of the last output policy of the training here. Well, in my experiment anyway. Something like this. Okay, now let's talk about the sim to real transfer. In my last video I explained how I set up my how the policy is running on the hardware, and then how the motors are being controlled. Actually, I'm still using the same method from the last video, so please take a look at that video for more details. But basically, the IMU is publishing data at 400 Hz using the 0MQ library, and the main policy is running at 50 Hz. And from the side, I'm also receiving the Nintendo Switch controller, in this case, controller inputs from ZMQ. So the policy is running at 50 Hz, looks at the IMU data, generates the IMU features, and then it outputs CAN1 and CAN2 data, and then these ones send data to each of the motors. Now the time requirement for CAN communication in my case is about 2 to 3 milliseconds per network. So total is about 3 to 6 milliseconds to get the current position and velocity of the motors from over the CAN network. So that's well within my 20 millisecond budget. Here is my run control. So this is my main loop right here. I first receive my controller data. So here's just a few things to start and stop the policy. So here is when the simulation, the policy is actually running. So the first thing I do is I get the latest motor data. So I send update motor position velocity command to my motors. This will take, as I said, 3 to 6 milliseconds. And so the the latest joint positions are received here. Last action is just last action, which is set at the end of policy. Here is IMU features. So this one is the raw. So I get the raw IMU data from the IMU, which is here, and then I separate it into acceleration and gyroscope rotation, and then these two are combined into the raw IMU data here. And this code here is calculating the gravitational vector, and this is exactly the same as the code that was running on the simulation. So that's IMU features. It's basically the same as the simulation training data code. And when I hold down the R2 button, then it runs the walking policy, and if there is no controller button clicked, then it runs the standing policy. So let's take a look at the walking policy. So the first thing I need to get is the current phase of the observation. So if we take a look at this, it's very simply just the cosine and sine of the current motion phase, which is just the time of the policy, current time of the policy, and then with respect to the walk cycle period, which is how long it takes to complete one cycle. I have a roll phase here, which kind of controls which part of the animation I wanted to start, which kind of becomes, it's not really that important, so you can skip that one. And the angle to target is the current target angle, which in straight walking it will be 0, but then it will change as the robot walks, and then the body's orientation changes. So the observation is the IMU features, joint position, joint velocity, last action, angle to target, and motion phase. And then I call the walking policy. So this one contains the policy models, and then I call it with my current observation. This is kind of a safety action clamping, so I don't want the angle to suddenly jump to some too large a value. So I just apply it as just clamping for safety. And then here we have apply actions. So the actions are sent to each of the motor with a scaling factor of this, and then we update the last action, and then we track the current motion phase of the robot, so with the time that passed. So that concludes the implementation section of this project, and let's next move on to the cost for this project. And if I missed something, please watch my previous videos, and if the information is not there, then I'm sorry, I probably missed it. So here's the cost for the project, and the total cost for me was about $4,000, or about 600,000 yen, which is my current local currency. And the most expensive parts were, of course, the motors, the 3D printer I used for this project, and the HGX computer. Let's take a look at some of the problems with the robot design. So it walks and stands fine, but you can see that the robot bends forward a little too much, and it's not actually supposed to do that. And the reason why it's happening is because I've used ABS filament as my leg material, and ABS is quite flexible. So here you can see that when the robot is supposed to be standing straight, it flexes forward just because of the material that was used. Now this is a problem because although the policy is supposed to bend forward a little bit like this, the reality is it flexes forward a little too much. So flexible material is not very easy, or I don't know if it can be simulated in Isaac lab, but the problem is the robot is expecting this kind of pose given the current joint angles, but the actual robot has a much different configuration. Especially the IMU is outputting values that is not consistent with what it's expecting to see. Now, another problem is I've ordered these bent sheet metal from an online service, but you can see here the angle of the bends are not actually the same, so it creates this error between this sheet metal part and this sheet metal part. So the robot's main problem is that there is a bit of a flex in the position of the robot, and the problem here is that when we try to zero the robot to this standard pose, it's not actually, the real robot doesn't assume this kind of pose. So there is a discrepancy between the trained policy's expected pose and then the real robot's expected pose. The second problem we see because of this is that the radius on the side of the leg is quite small here. I don't remember what exactly the value is. I think it's maybe 5 centimeters or 5 millimeters, I don't remember. But that means if there is a small error on the position of the side of the leg, then that becomes kind of a big error if it kind of overturns this side just slightly a little too much, and then it will stumble, and that's why you see the robot stumble from in the previous video. So one thing that would be better in my opinion is to, instead of using 2 of these cylinders as the bottom, it's probably better to use one large radius so that a small error doesn't cause it to stumble, and it will still be able to recover from that kind of errors. So as usual, the video has gotten a little long, so let me give a quick conclusion and then do some lessons learned from this video. So in conclusion, in my series of videos, I've shown how to do a design of a robot and how to design software and hardware parts of a robot, how to do the reinforcement learning training, and then how to transfer the simulated policy to real robot. And I think for this video, I think it's a partial success. The robot walks, it stands in balance, but as I showed you, it has some problems with the design itself, which cannot really be solved through the policy training. And I need to redo the design to deal with this. And on top of that, there is still quite a lot of left to do and tune, but as a proof of concept on how to do all of the top line, I think this is a partially successful project. So some of the do's, these rope stride motors, they're good enough for a demo robot. I think it works well enough. They're quite cheap. And in my previous video, I used RS485 as my communication network, and I said it has some real serious problem with communication speed. And using CAN network has actually dealt with the problem. So use CAN network whenever you can. Here are some don'ts. If you're going to use plastic 3D printed parts like I did, don't make a 1 meter tall robot. It's better to design short robots so that it's much easier to balance and you don't have to worry about flexing. Also, you should use lightweight motors so you don't have to deal with, again, flexible plastic. I think using rounded shoes is better for stability. When there are errors, it doesn't become a big error if the side of the shoe is much rounder. And one thing I learned is it's better to incorporate sheet metal parts really early in the design. I think the sheet metal parts were really cheap to order. I think it was maybe $20 to $30 per part, including shipping. So that was great. Okay, and that's it. And I hope you learned something. And I learned quite a lot by doing this. And I think I will continue on if I have some time. Thank you for watching the video.